Hello viewers, welcome to today's session. Today we are going to discuss about the combinations of resistance, inductance and capacitance when connected in series and parallel. First we will start with resistors. The resistors connected in series R1, R2, R3. When the resistors connected in series, a voltage V is applied, then the total voltage V equals to voltage drops across R1, R2, R3 sum. And from the series concept, the current flowing through all the elements will be same. So this is the fundamental point that you have to remember while solving series and parallel circuits. The current in series elements are same, and when we write the equation for voltage across resistor, V equals to I into R. Total voltage V equals to I into R1 plus I into R2 plus I into R3. Why? Because current I1, I2, I3 everything is same, so I have mentioned it as I. And total voltage V equals to I into R equivalent or R total. From this, if we take V common, V gets cancelled, we will get R equivalent equals to R1 plus R2 plus R3. This is about series circuits. And next is when resistors are connected in parallel. So the resistors are connected in parallel, the current divides in each resistor. The total current equals to the current in resistor R1 plus current in resistor R2 plus current in resistor R3. And in parallel combination, the voltages are same. The voltage from the source equals to voltage across R1, voltage across R2, voltage across R3. Everything is same. This is the basic difference between series and parallel resistors. In series circuits, current is same. In parallel circuits, voltages are same. So the total current I equals to I1 plus I2 plus I3, where I equals to V by R from the Ohm's law. So V by R total equals to V1 by R total R1 plus V2 by R2 plus V3 by R3. If V gets cancelled, we will get 1 by R total equals to 1 by R1 plus 1 by R2 plus 1 by R3. These are some of the series and parallel combination of resistors that we can see practically, just like refrigerators. This is how we can observe in refrigerators. Resistors are connected for bulb and motors like this, and series and parallel resistors combinations. And next, coming to series lighting systems also, every bulb will have some resistance. In series, number of bulbs having number of resistances, the total resistance will be calculated based upon the equivalent resistance for series combinations. So for this, while solving series and parallel combinations, both this kind of circuits you can observe. For this series and parallel combinations, while solving, you have to remember one point is where the elements having the current flowing through these elements common, those are series elements. Where the current is divided in the elements, these are said to be parallel combinations. So based upon the concepts of series and parallel combinations, simplify those resistors according to series and parallel concept. Next, when inductors are connected in series and inductors are connected in parallel. When inductors L1, L2 up to so on are connected in series, the voltages are different. As we know in series concept, voltages are different. Total voltage across inductance equals to the voltage across inductance 1, 2 up to so on. So VL equals to VL1 plus VL2 plus V up to so on. And voltage across inductor VL equals to L into di by dt. So from this, di by dt is taken common. So we get, as I is the common, so di1, di2, di3 all are equal to di by dt. V equals to L into di by dt equals to L1 into di1 by dt plus L2 into di2 by dt plus up to so on. and I is common, so di by dt gets cancelled. L equivalent equals to L1 plus L2 plus up to so on. So in series the inductors are added, and again similar to series combination, in parallel also the inductors are connected in parallel. Then the equations for inductors connected in parallel will be I equals to IL1 plus IL2 plus up to so on, and IL is nothing but 1 by L integral of V of t dt. Similar to this, IL1 equals to 1 by L1 integral of V1 dt, IL2 equals to 1 by L2 integral of V2 dt, like this. And in parallel combinations voltages are same, so 1 by L equivalent integral of V dt equals to 1 by L1 plus 1 by L2 up to so on into integral V dt. So we get 1 by L equivalent equals to 1 by L1 plus 1 by L2 up to so on. So like this, in parallel combinations inductors are calculated. Next, these are some of the practical inductors that we can observe. So this kind of fan windings also we can see the inductors how it is wounded, and in some cases just like first order circuits, like speakers arrangements for listening voice, like this also how we will connect inductors and capacitors, combinations of series parallel inductors capacitors. And again in transformers also we will see how the inductances are placed, primary inductance, secondary inductance, like this. And in some sensors also this is the way to provide the inductance values for the receivers. We can see the figure how inductance is placed, how it is producing the magnetic field. And again like Hartley oscillators for electronic circuits, we can see inductance placements like this. So these are the practical connections of inductances combinations, series and parallel combinations. Next is capacitances, when capacitances are connected in series and parallel. So in capacitors, when these are connected in series, we can see the combination of these series capacitances applied by a voltage source. This combination will be having the equivalent capacitance C equals to Q by V. This is the formula for capacitance for a charge per unit voltage. So V by Q equals to 1 by C1 plus 1 by C2, where 1 by C equivalent equals to 1 by C1 plus 1 by C2. So this is when capacitors are connected in series. That is, we know from this C equals to Q by V equation we will get this 1 by C equivalent equals to 1 by C1 plus 1 by C2. So that is difference between resistance inductance series combinations and capacitance combinations is opposite to those two. In resistors R1 plus R2 plus R3 directly added, in inductors L1 plus L2 plus L3 directly added, but in capacitors 1 by C equals to 1 by C1 plus 1 by C2, like this up to so on. Next, coming to when capacitors are connected in parallel. So like this we can observe the capacitors connected in parallel. So when capacitors are in parallel, from the concept of charge Q equals C equivalent into V, the capacitors charges Q equals to Q1 plus Q2 plus Q3, which is equals to C1V plus C2V plus C3V. So total equivalent capacitance can be equals to C1 plus C2 plus C3, where V gets cancelled on both sides. So this is when capacitors are connected in parallel. And also we can see the practical applications of these capacitors like electronic circuits, radios, TVs, amplifiers. In every circuits connections we can call it as a filter also, capacitor filters we can utilize in practical purpose. And this is how we can see in some heat sinks also. In heat sinks we can utilize this capacitance for series and parallel combinations like this. So this is about series and parallel combinations of resistors, inductors and capacitances. Based upon these concepts, you have to solve the series and parallel combinations of these basic parameters. And in next video I am going to explain voltage sources, current sources of independent and dependent sources.